leave my earbud in here. So decoders take binary and convert it over to the other bases, right? So we can go to BCD, which is not a base, but we use BCD so much because it gives us decimal numbers, and we're a decimal species. By the way, another thing they do in Germany is where we use dots in the number, they use commas, and where we use commas, they use dots. So $3. That took a little while to get used to. Yeah, so $3.33 would be 3,33. So that's the way they do in Germany. And if it was 3,300, then they would put a dot right there. So they use a dot where we use a comma, and a comma where we use a dot in the numbers. And they've changed. They use the Z. Z is one of their vowels. So it's one of their predominant keys. So they swapped the Y and the Z key on the keyboard. That was fun. So a lot of the stuff that we did, we had to do on their computers. And the Y is where the Z is supposed to be, and the Z is where the Y is supposed to be. So they use the Z. It's one of their predominant letters. There's a lot of Z's in the German language. Plus, they got the keys. They got the A with the two dots on the top, and they got the U with the two dots on the top. That's on their keyboard. So sometimes they gave us out their computers to use some of their stuff, and that was fun. So you'd be typing along, you'd have these words. So we have an encoder. And an encoder takes another base and brings it back to binary, right? Y'all understand that? So a decoder takes binary to another base. An encoder would take another base and bring it back to binary. So we have a decimal to binary, decimal to binary encoder. And the one we'll look at, and the only one we'll play around with, is the 74174. I think there's 138. By the way, the book doesn't use, they use national semiconductors, and national semiconductors don't do things according to what everybody else does. So 7442, we went over that. 74154, we went over that. And then 74147, this is a decimal to BCD encoder. It's also a priority encoder. So that means, we'll look at that in a minute. So this is the 74147. This is the truth table. I don't like using the truth tables in the book. I like using the truth tables that we get on a data sheet, right? You understand? So let's go in the Blackboard and let's find the truth table. I mean the data sheet for a 74174. Should be listed in there. So this brings in 10 lines of decimal, but remember on a decimal, we have one, we're going to represent this with one line. Does that make sense? So like what we get out of a 7442. So I have a 7447 and 7448. So 7447 goes from decimal to BCD. A 74, what did I say? A 7447 goes from decimal to BCD. And 7448 would go from octal to binary. Everybody okay? Now what they mean by a priority encoder is, we'll see what that means. So here's the 7447. So if I bring, here's my 10 inputs, 9 inputs. So if all these are high, they assume that the 0 is low. Does that make sense? So all these are high. Notice all my outputs go high. If I come in here and put 9, then the D output goes low. So these have low active inputs, right? You'll understand that, yes or no? What do you mean? Well, it's a 9. So I'm sorry, it's a 9, but these are low active. So excuse me. So if these are low active, then this is true, and this is true, and these two are false, right? You'll understand that. So if this is true, that's 2 to the 0. If this is false, if this is true, that's 2 to the 3rd, so that would be a 9. So now you got to see things backwards, right? Because it's a low active output. But look, if 9 goes low, what about all the rest of them? They don't matter. So that's what they're talking about, a priority encoder. So 9 has the highest priority. So if 8 is low, what if 9 goes low? Well, 9 has the highest priority, right? You understand that. That's why they call it a priority encoder. So 8 has the second highest priority. And notice the D output went what? Low, which is an 8. You got to see this upside down, right? Here, if the 7 goes low and the 8 and the 9 have to be high, they are not don't cares, because the 9 has a higher priority than the what? Than the 8, and the 8 has a higher priority than the 7. So we can use this as a priority chip too if we want to do that. I can bring 8 inputs in there, and whatever I want the highest priority, I can hook it up to the 9, right? You understand that? And my lowest priority, I'd hook it up to the 1. And it takes for granted 0. So notice here, it's not a 9, it's not an 8, it's not a 7, it's not a 6, it's not a 5, it's not a 4, it's not a 3, it's not a 2, it's not a 1. So it's got to be a what? It's got to be a 0. So all the outputs go high, right? You understand? That makes sense. Okay, and then right down the line, so I'll come in there, I put a 6 in here, and this would be a binary 6. I come over and put a 5, this would be a binary 5. So you see what it's doing. It's taking the decimal number like out of a 7447, I'm sorry, 7442, which has low active outputs, and converting it back into binary for us. Oops. So I think I got it set up like that, 74,147. So here we have a 7442 that's doing what? It's taking binary and converting it to decimal. And then I'm taking the output of these circuits really get. But you got to understand, this is a lot of circuitry. It takes a lot of wires. Looks very impressive. So here, this is let's see if I can make it smaller. So here's my counter. So I'm using a counter. How am I counting with? I'm counting with a switch. So we'll talk about counters later on. I'm taking the output of my counter and I'm inputting it into 7442, which is a 4 to 10 decoder. I'm taking that and then I'm displaying that here, and then I'm taking the output of the 7442 and running it into a what? 7447. Let's see if this works. So right now I'm bringing in a 0 into the 7442, and it's telling me what? 0. All the outputs go high because these are low active outputs. So when all the outputs are high, it's decoding a 0. Okay. There's a 1. This is a 1. Here, this is decimal. This is back to what? Binary, but low active. So if I needed highs, I'd have to run these through an inverter, right? You understand? So what you need to look at is the light turned off is a true, right? Okay, here's the next count. My decoder sees a what? It sees a 2. Output 2 went low, and over here this encoded it back to a what? To a 2. You understand what I'm doing? Yes or no? Huh? This is a decoder. This is low active. So what happened on what? This side? Yeah, this is low. Yeah, but this is actually the true binary number. So this is the true binary number. This is a 2. But the problem is the 7447 has a low active output. So the counter is a high active output. So that means it's true when it's what? When it's high. The 74147 has a low active output, so it's true when it's what? Low. So notice this is just the opposite of that. So this is a 2 using high active logic. This is a 2 using low active logic. And a lot of these decoders and encoders are low active outputs. Why? Because they can provide more drive as a low than they do for a high. So the 7442, so these LEDs are high. These guys turn on. These guys light up when they see a high. So the 7442, I'm inputting the 2, and the 2 output is actually going low. That's why the LED turns off, right? You understand that? But then this guy's taking this decimal and converting it back over to inverted binary, right? You understand that? So here's the watt over here. This is actually the true binary number. That's a 3. What output is selected? 3. And what output is selected here? A 3, right? Y'all understand that? Yes or no? Okay. So there's a 4. There's a 5. There's a 6. So what we're doing is we're using a 7442 to go from binary to BCD, and then we're using the 7447 to go from BCD back to binary. But it's low active binary, which means a 1 is actually a low, right? Does that make sense? So is a 1 always a high? No. It all depends on whether you're dealing with low active logic or whether you're dealing with high active logic. And we talked about that at the first of class, right? About what is a 1 and what is a 0. To get a 1 and a 0, you just got to have 2 different representations. So I could say my hand is up as a 1 and my hand is down as a 0, or I could just as well say what? My hand is up as a 0 and my hand is down as a 1. So digital can be represented as low active logic or it can be represented as high active logic. It all depends on the system. You can see on these guys, counters, of course, use high active logic because they're counting. But these guys right here, both these have low active logic. They're low active. Because why? Because they can drive more for a low than they can what? For a high. So there's a 7. So here's a binary 7. Output 7 went low. I took the output of my BCD decoder, brought it into my encoder, and it converted it back into a 7. Okay. There's an 8. There's a 9. And now we're back to illegal, right? Or not illegal. It's just that we're out of the range of the encoder and we're out of the range of the decoder. So what does a decoder do? Well, it takes binary and converts it over to something. BCD or hex or octal or 7 segment. So a 7447 is a decoder. So what's it doing? It's taking binary and converting it over to a code that runs a 7 segment display for you. So all I do is put a binary number into the thing. So if I had this counter and I was feeding it into a 7447, I put a 0 in there, it would turn on to the segments to display a what? A 0. If I hooked it up right. If I don't hook it up right, it does weird things. And it looks very impressive though, don't it? But it would be a lot. It would still take the same amount of wire, or even more, to hook this up using basic logic gates, right? You understand that? So we do this so often that they integrate the thing into a single wafer. Wrong computer, Rich. I'm switching between applications. Of course, y'all know that y'all can hit Alt-Tab on your keyboard and switch between applications when you got multiple applications running. So you can bring any program you want to the what we call the foreground and still run it full screen. Okay, so that's decoders and encoders. Y'all okay? What about multiplexers? What is multiplex? What's media? Media is what information travels through. So what media am I using right now? What media am I using right now? I'm sitting here talking to you. What medium am I transferring my information from my mouth to your ears? What medium am I using? I'm reading it right now. I'm using air. So air is the media, right? You understand? That's the media that I'm using right now. It's what information. Like a lot of people say, what am I medium am I using? They say in your voice. My voice is not the media. The media is what information travels through. Okay, you'll understand that. So multimedia computers means they either send it, the media is always air, but still call it multimedia. So newspapers are media. So what's multiplexing? It's when we let multiple information or more than one type of information share the same media. What's the two types of multiplexing? Y'all listen to the lecture. What's the two types of multiplexing? People in networking, we call them baseband and broadband. Have you ever heard of those terms? What does that mean? What's broadband? What's broad? Well, you don't know what it means. It's a term you throw out there that sounds impressive, but you don't know what it means. Well, you're going to learn. These are also called time domain. Technically, in digital, we call them time domain multiplexing and frequency domain multiplexing. So with Ethernet, we're Ethernet. Ethernet is baseband. The Internet is broadband. Ethernet uses time domain multiplexing. Broadband uses frequency domain multiplexing. What's the difference? What's baseband? What's the baseband? We only have one device on there at any one time, but that one device gets the whole bandwidth of the media. So all media has what we call a bandwidth. A bandwidth is the range of frequencies a media can reliably pass. That's the bandwidth. That makes sense. So we work with bandwidths all the time. If you exceed the range of the media, then the media can't support it anymore, right? Air's got a really good broad base, got a really good bandwidth. In fact, the bandwidth of air is so big that we subdivide that into bandwidth. So we have extra low frequency, we have low frequency, we have high frequency, we have ultra high frequency, we have extremely high frequency. We got all these things that they divide that up. Copper wire has a lot lower bandwidth range than air. Air's got a really good bandwidth to it. So what they do is they subdivide that into frequencies that you stay inside of to keep that range. So what they do with time domain multiplexing is that one device is on the network or on the media at any one time. But when that device is on the network, it's got the entire bandwidth of the media. So that means if we're dealing with gigabit Ethernet, then by George, if you're on the network, you can do 1 billion bits per second. But the problem is, who else can get on there? Nobody. So the way Ethernet works is they divide the information up to packets, and it's 4,096 bits per bytes per packet. So what happens is you come up there and you're on the network. You send out a packet, then you come off the network. And what Ethernet uses, it uses something called carrier sense multiple access with collision detection. So everybody's sitting there listening to the network. As soon as the network comes free, That's when they all try to do what? Get on there. If they get it first, and then the other guys back off. If two guys try to get on at the one time, you have a collision, and they both do what? They back off. So everybody's sitting there. So everybody's in here sitting there. You got your Wi-Fi on right now. Everybody's sitting here listening for when it's free. Now, what's nice about that is how many of these computers are on the network at any one time. How many of y'all on the network right now? None. Y'all not doing anything. You're not transmitting data. You're not, when we say on the network, we don't say listening to the network. I mean, how many computers in this lab are trying to put information on the network right now? None of them. Your phone's not trying to put information on the network unless you go in and you try to like access the website, right? You understand? When you access the website, it's going to give you 4,096 bytes. It's going to come off. Somebody else is going to grab it. You're going to listen. When it comes free, you will get 4,096 more bytes, right? You understand? So that broadband, if there's like nights, baseband like nights when there's very few people on the network, it's great. 7 o'clock and 8 o'clock in the morning when everybody's checking their email, you're constantly doing what? Listening. It's hard to get the pace, and so it slows down. So as far as speed goes, baseband has the advantage of being the fastest speed with the fewest people. Now, broadband, what they do is they put your information on a carrier, so you're modulated. So it puts your information on a carrier. And what happens is there's so many computers that's assigned a certain bandwidth inside the bandwidth. Does that make sense? So if you got a media that's got a 10 megahertz bandwidth, and then everybody signed 1 megahertz, then you could have 10 computers on the network at the same time. If you're on there by yourself, you get 1 megahertz. You understand that? If 2 people's on there, you get 1 megahertz. So your bandwidth never changes on broadband. You get the same bandwidth all the time. But the problem is that, okay, how do they divide that bandwidth up? And then, of course, if you're the 11th person, then you got to wait for somebody to do what? Get off. But you have a better chance of getting on the network when it's a lot of traffic on it. So the internet is baseband. I'm not broadband. So broadband, you got multiple devices on the media at the same time, but they're all on a carrier. You understand carriers, right? What's a carrier? What's a carrier? No. We're talking about communication. What's a carrier? A carrier is a high frequency signal that you place lower frequencies on top of. So when I go out, and it's really comes into play when you go out there and start tuning the radio in your car. So you got a radio station that you listen to. What radio station do you listen to? What's the frequency? Most of y'all just on the dial of your radio. When you tune in a station, it gives you FM is in megahertz, right? What's that? The frequency? Is that the information? No, it's the what? It's the carrier, right? You understand? So is that broadband or baseband? Broadband. You got all these stations out there riding on the same media at the same time, right? And that's multiplexing. But if you're going to multiplex, you got to be able to do what? Demultiplex. If I couldn't demultiplex, then multiplexing wouldn't do me any good. Wouldn't that be awful? You know, you multiplex your cell phone and your cell phone rings and you got 1,000 people on there at the same time trying to talk to you. Or you're out there at Bryant-Denny Stadium or down at Jordan-Hare Stadium on the 50-yard line when Alabama and Auburn's playing, and you're trying to listen to your buddy up there on row 50, seat 37. Are you going to ask multiplexing? So when them crowds get in there, that's multiplexing, right? You understand? Can you understand what anybody's saying? No, all you hear is just one big roar because you don't have the ability to demultiplex. Now, what could you do? You could pick up your cell phone and call them, and now you can talk to them. So now you have the ability to demultiplex. So if I'm on a multiplex, I'm going to what? Have to demultiplex. A baseband or broadband, we use something called a modulator, demodulator. And just about everybody calls those things what? Modems. You have a modem on your cable if you've got your internet. Now your TV demultiplexes for you. So when you select a channel, it selects a carrier, right? You understand. Your internet, though, if you got internet, you got a what? You got a cable. What do they call them? Cable modems. So the process of putting information on a carrier is called modulation. The process of stripping the carrier off and letting the information come through is called demodulation. So we call those things modems, short for what? Modulators, demodulators. Now digital, luckily digital is nothing but baseband or time domain multiplexer. So all our multiplexers that we're going to talk about in this class are going to be time domain multiplexers. And what do we use multiplexers for? What do we save with multiplexers? So how many channels do you have in your TV? If I didn't demultiplex, that means we would have to have a cable for every channel. But I've got one cable. So what does multiplexing save? Saves wire, saves media, right? You understand? Saves media. And so sometimes we sacrifice speed for cost. So heck, if I was to take my computer and hook it up directly over there to my server, then by George, I could communicate real fast, right? You understand? But what would be the hassle of that is I would have to have one wire to running from every computer back to my server. Not to a switch, but I'd have to one wire. So we come up and we do what? We multiplex. It allows us to do what? Save wire or save media. Could y'all imagine trying to pick up radio in your car and you had to have wires running from a whole station coming into your car? So, once they figured out how to send information through the air, it didn't take them very long to start figuring out, okay, I can come up here and I can set these things on a carrier. And then in AC, you'll learn about tuned circuits. Tuned circuits are circuits that we can build that allow one frequency to come through and blocks everybody else. So that's what you're doing when you're tuning your radio, and they call it a tuner, right? Because you're setting up a tuned circuit. So what happens is when you dial in 93.7 megahertz, you're setting up a tuned circuit that only lets that carrier come through. And then once the carrier comes through, we have circuits that strip off the carrier because it's a real high frequency. So we run it through what we call filters. We strip off the carrier and we let the information come through. And that's basically the way radios work. So that's the nice thing about frequency domain multiplexing is everybody has a chance to get on the media, right? You understand? It's your band. So every radio station out there has got a bandwidth that they're assigned. FM is around 15 kilohertz per station of bandwidth. AM is like 5 kilohertz per station, and that's their bandwidth. They're allowed, but they all get what? So they can all be on there at the same time, but they have to share that bandwidth, right? You understand? So each one of them is assigned a certain range of the bandwidth that they can get on there. So that's why AM is so bad, because it's only 5 kilohertz. Really, the AM station. Not so much anymore. Radio still pick them up. FM is 15 kilohertz, which is really, really good. So that's the bandwidth that every station gets, and that's monitored a lot because these stations are right next to each other. And if you spill over, if you do 17 kilohertz, then you're going to do what? You're going to get into somebody else's station. And you hear that every once in a while when you're traveling And so FM only travels so far, right? You understand that? Have you ever been where you pick up more than one station at the same time? Well, what is they're inside the what? Inside the sign bandwidth. So multiplexing and deplexing, very, 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 very important. What does digital use? Digital circuits we use. There's our 7-segment display guys. So multiplexing. Signals share the same media. Multiple signals share the same media. Time domain multiplexing. Only one signal on the media at a time. Each signal uses the entire bandwidth of the media. 3C domain multiplexing. More than one signal shares the bandwidth of the media at a time. And each signal is riding on what? On a carrier, not a ship. Baseband, broadband, you understand that now? So baseband, this is time domain multiplexing. Each device uses the entire bandwidth of the network. Your telephone system is baseband, Ethernet is baseband, USB is baseband. Broadband, also called 3C domain multiplexing. Several devices share the bandwidth of the network with transmit data. Television, radio, cable, T-carrier, cell phones, these are all what? These are all broadband. Are we okay? Make sense? So y'all know what broadband is. How many times y'all heard that term? Selling bandwidth. So your cable companies, all they got to do is just give you a little more of the bandwidth, right? You understand? So, but you pay more for that. So when you join these cable companies that's got internet, you get a basic bandwidth, but you can always do what? You can pay more for it. They should give you a little more space of the total bandwidth of the network. So this is basically what a multiplexer does. So we got some pins that are going to call select pins, and we electronically select which input is routed to the output. So if you understand this, you understand multiplexers, time domain multiplexers. How long is it going to be there? Well, it's going to be, so if I come up here and put a binary 0, then what's it going to do? It's going to switch up here and let what signal come through? It's going to let 0 come through and go to the Y output. If I come up here and put a 3, then this thing is going to electronically move down to there, and it's going to let that guy come through. And this is all a time domain multiplexer is. Except Ethernet don't work like that, but it's kind of strange. What we do on Ethernet to decode is we use, it depends on what you're transporting on. Of course, everybody's familiar with TCP/IP, right? You ever heard of that? You probably heard of this, IP. This is the way we address, and this is the way we actually transport. So TCP defines the size of the packet. It defines all that. IP is the way we multiplex and demultiplex. So every computer on an Ethernet network has a what? Has what we call an IP address. Well, actually, that's kind of true. The IP address is a logical address. There's another address that's built into every network card. It's called a medium access control. And this is the address, this is the physical address of the card. Most people call this the MAC address. And this is a 24-bit binary number. Is it 24? No, it's 48. This is built into the card when this is assigned when the manufacturer puts your phone's got a MAC address. You ever looked at that? The MAC address? That's the physical address. The IP address is a logical address. It's assigned by the network. And what happens is these guys right here keep up with that. So this is what we call a switch. So as soon as I come up here and hook this network up to that guy right there, the switch, what it does is it goes out there and matches, it records my assigned IP address and my MAC address. So the MAC address is your physical address. Does that make sense? Which is pretty neat. We got two versions of IP. Well, what's the two versions? We got IPv4. Anybody know what that is? That is a 32-bit binary number. And they realize that most people don't understand binary. So they give it out in what we call a dotted quad. Each quad represents 8 bits, like 172.25.60.53. Well, what this is a byte. That's all it is. And if so that'd be 4 times 8. That's 32 bits. So it's a 32-bit number. But they understand that most people don't understand binary. So your computer converts this over to what for you? Converts it over to decimal. That's a 32-bit. And this became known as IP. Some people call it a dotted quad. You ever heard call that? How do we get these things? These are assigned to us. We got 2 ways we can assign them. We can assign them either what we call static, which means you keep one and you assign it and your computer always uses that, or you can use what we call dynamic. Dynamic, we use something called a DHCP server, Dynamic Host Configuration Protocol. And what happens is that your computer comes online, it broadcasts out, I'm online. The DHCP server inside your network picks up on that broadcast and then sends you an IP address that's not being used. Well, it depends. Static IP stays the same. Dynamic IP, when you set up a DHCP server, you set up a lease time. So you can set up a lease time, which means if you leave your computer on all the time, you'll keep the same IP. But if you got a lease time of like 2 weeks, that means you can turn your computer off for 2 weeks and you keep the same IP. If you don't turn it on in 2 weeks, you get a what? So guess what happened to me? My computer locked up on me. I was gone for 2 weeks. So now I came back and guess what? Got a new IP. Of course, I could probably give it a static IP already. They give us a range of static IPs. Our department's kind of special. So we have a range of static IPs we could use if we want to. So your servers, you have to give your servers a static IP. You can't give them a dynamic IP or your servers would keep doing what? Yeah, move around if you ever lost power. So what we do is this is the way we multiplex and demultiplex with these. So the IP address is part of the packet. So so we don't have a so even though it's time domain multiplexing, the address is inside the packet, and your routers and your switches move those packets around according to those IPs, right? The last switch, by the way, keeps up with the MAC address. So the MAC address is physical. It's a 42-bit number, 48-bit number, which is a lot of, how many MAC addresses can we have? That's 2 to the 48. So we're not even running out of MAC address. The problem with the IPv4, that's 2 to the 32nd, which seems like a lot. But think about how many IP addresses you're using at your house. And then they've got some that's reserved. So the government's got their IP addresses reserved. We have what we call private networks, which have a range of IP addresses. So if these computers ever got out on the internet, they'd go nowhere because they're not legal internet IP addresses. So this 172.25, we call those private addresses. Those are inside, right? You understand? And then we have what we call a gateway, which has the IP address for the college, which is pretty neat. So private IPs, then we have government IPs, then we have testing IPs. So what happened was they started running out of these IP addresses. So what did they do? Well, they came out with an IPv6, which is anybody know what it is? It's huge. It's more than 64 bits. And it's weird too, because they split up hexadecimal, so they use hex instead of using dotted quads. They use 4 bits of hex, 4 digits of hex, which gives you 65,536. But the last 8 are always these dotted quads. You ever seen an IPv6 address? Let's see if this computer's got one. Usually you get both of them. By the way, we'll never, ever, ever get rid of command prompt, because just about all your networking applications, TCP/IP, runs off of this. So you can bring up DOS prompt and you can type in IP config, and what this will do, this will bring up all the IP information about your networking. So disconnected. So here's the information. Here's the IPv6 address. So look what they use. So up here, this is what base? So that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And this would be 8 bits back here. This is kind of so this would be, that's 4 times 16. How big is that? 128 bits. So we should be able to use this forever. Here's my IP. This is my IP. This is my IP address, IPv4. But this is called a subnet mask. Anybody know what subnet mask does? Well, what a network is divided into, it's divided into subnets, and then it's divided into computers that are on the subnet. So the subnet mask tells us what part of the IP is the network ID and what part is the computer ID. Does that make sense? So the all ones is identifying the network ID. So that means this would be the network ID. This down here would be the computer ID. That makes sense. 512 computers on this subnet. Because this is a 4, so that means the last bit would be a 0. So this would be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So if you don't understand binary, you can't do subnet math because it's binary. This is the default gateway. Default gateway is the address that takes you out to the internet. But that's an IPv6 address. How long do you think it's going to take before we run out of those? Yeah, I don't think it'll be in my lifetime or your lifetime. We're slowly moving over that too. You can see inside here, though, it's predominantly here. So what happens, every packet I send out, this IP is on there. And this goes out through the network. Originally, the IP and the MAC's on there. The first switch grabs the MAC and keeps it, so the MAC never goes out on the address, never goes out on the internet. The only thing that goes out is the IP address. Then this thing starts routing around through these routers and all this other kind of stuff, right? Does that make sense? And finally gets to the computer that you want to talk to. The computer says, okay, this is this IP address. When I answer, I'm going to use what? This IP address. And then they answer that IP, and it comes back. It is TCP/IP is what they call I forgot what they call it. And then it finally comes back to this guy, and then this guy says, okay, this IP address belongs to what? To this MAC address, and that's how it gets to your computer. So that's the way this guy here did it. Okay. The what? Internet of Things. Oh yeah, and we can do that now that we've got all the IP addresses to deal with. For years they used what they call Bluetooth was originally developed to hook up appliances. That's what Bluetooth was developed for, to bring smart appliances. Of course, you can see where that went to. We use Bluetooth for a lot of stuff now. Bluetooth's interesting in itself. Uh, by the way, a lot of y'all don't understand IPs, so what do they give us the ability to use? We call them URLs. They're technically called URLs, which is Universal Resource Locators. Most people call them names. So what happens is we have these things called DNS servers, domain naming system servers, and those. You remember old phone books? Of course, I do that right now. So I don't hardly know anybody's number because I have them stored under a contact, right? You understand? And when I say dial my son, John, my phone keeps up with the number. So that's what you're doing when you designate a COM. So we have COMs, we have EDUs, we have business. Well, what you're doing is you're designating what we call a DNS server. A DNS server is like a phone book. So what does it do? It matches a number to an IP address. So as soon as you put lawsonstate.edu, then there's no IP. So what does it do? It goes to the DNS server that handles the EDU accounts, what we call the domain, right? It goes in there and says, okay, lawsonstate.edu is this IP address. And then it's the one that's actually attached in the return IP. So what it does, DNS servers allows us to what? It allows us to use names instead of what? Instead of numbers. So as soon as you type in .edu or .com or .anything, and then you got countries that's got .com. So you got like, we're lucky to have the .com. If you was over to Germany, you would have another little old designator .com. So that means that would send you to the DNS servers for .coms and what? In Germany, if it don't find it there, and so if you put like Intel.com, it wouldn't go to Germany's DNS servers, it would go to what? It would come over here to ours. So all your other countries have designators that indicates that that's the DNS server for their country. So if you put, and every country's got a little 2-digit code for every country, so you'd put like something dot, like UK, you'd say UK.com, and then so now you're not even going to hit the DNS servers here. You'll go straight over to England and hit their DNS servers over there. So DNS servers, so y'all learned a little about networking. I'm sure y'all always wanted to know that, and so we spent a lot of time for multiplexing. So this is basically the makeup of a multiplexer. Do we need to know this? No. All we need to know is a multiplexer. So let's look at the 74151. How are we doing on breaks, guys? Y'all know I get started up here. So if we need to take a break, then somebody needs to do what? Okay, so let's take a break. Let's look at a 74151. I think. Let's make sure I'm ready. I'm pulling these chips off the top of my head, by the way. That's why you learn a lot about them. So this is a 1 to 8 line data selector multiplexer. And these are time domain multiplexers. So what these guys are going to do, it's going to take 8 data lines and route them over to 1. So that means I'm going to be able to send 8 signals on how many wires? One wire at the same time? No, it's time domain multiplexing. So this is showing us, this is the guide. Here's my data inputs. We have D0 to D7. Then we have my selectors. So the selector is selecting which input is routed to the output. Then we got strobe. This is another name for chip select. So if this thing's going to work at all, the strobe pin has to be what? Has to be low. We have two outputs. We have Y, which is uninverted, and we have W, which is inverted. It's up to you to figure out which one you want to use. Y'all understand that? So when I come up here and put, if strobe is high, then your ABC pins mean what? That means nothing, because the chip is not selected, right? So the Y output would go low and the W output would go high. If I bring the strobe low and I put put lows on my ABCD input, then D0 is going to be routed to the Y output or the W output. It's just that the W output would be inverted. Y'all understand that? Yes or no? Why don't you understand? Yeah. A is least significant. C is most significant. Okay. So this would be a binary 0. This would be a binary 1. This would be 2. This would be 3. This would be 4. This would be 5. This would be 6. This would be 7. Here's my data input. So data inputs. This is what data you want to multiplex. So whatever I would put, one of my signals I want to multiplex would be on D0. Then one would be on D1. One would be on D2, D3, D4. Okay, understand that. So when I come up here and I enable it, how do I enable it? I bring the strobe low. Then I select 0. So that's a 0, right? You understand? Then this is going to let D0 go to the Y output. Now D0 is going to go to the W output, but it's got the not bar above it, which means what? So if D0 was high at that instant, this guy would go high. This guy right here would do what? Go low. So that means if I came over here and I had this signal right here on D0, which on this one they're calling N0. So let's say I came over here and I was doing this. And then I came over here and I put all zeros on that. And let's say on this one, I was doing something that looked like this. Right? On this one, I was putting a signal on there that looked like this. Well, if I put zeros, then what it's going to do, it's going to let this input go through and go through this output right here. So what would happen is this output right here would be doing this. This output over there would be doing this because it's what? It's inverted. But it's still the same signal, it's just switched around. It's up to you which one you want to use. Which one do you want to send down line? If I came over here and put this on the select inputs, see if I'm still erasing. I've only got 3 of them in here. So let's say I come up here and put a 2 on there. So a 2 would be this, right? I put that on the inputs. Then what's that going to do? It's going to let this signal, since this is hooked up to input 2, this signal is going to be routed to here. So it's going to be doing what? It's going to be doing this. And this output is going to be doing what? This, because it's inverted. So what I do is I come up what input I want to pass through to the output. I select it with the select pin. How many inputs can I route through at any one time? Only one. But if I had a counter over here just counting, oops. Then what would happen if this counter was counting at an even number of times, then what would it do? It would switch. It switch one over, one over, one over, one over, right? And then when it got down to three ones or seven, it would just roll around and keep going. Now, what we'd have to do on these multiplexers is we'd have to send this, and we'd also have to send this, because if my demultiplexer is going to have to know how to select the right one to demultiplex, right? But you got to understand, it's still going to save you money, because over here I'm using how many wires for my data? I'm using 1, 2, 3, 4, 5, 6, 7, 8. How many wires am I sending it on? I'm sending it on 4. Well, I'm sending one data wire, but I got to tell my demultiplexer how to demultiplex. So if I'm sending 0, I got to tell my demultiplexer that this is 0, right? You understand? But what I just did is I saved 4 wires, which you don't seem like much. But when you're talking about copper, you're talking about a lot of money, right? You understand? So if I sent 16 wires, I could send 16 signals on 5 wires, because all I have to do is add another line. Right? You understand that? 4 for select, 5 wires. 4 for selecting, 1 for the data. So the more you multiplex, the more efficient it gets. And this is used all the time on slow things that move slow, that we don't need speed on. We do a lot of multiplexing, because what does it save? It saves a lot of money. And sometimes we multiplex because it would be just too expensive. So this entire network is multiplexed, right? You understand that? If it wasn't multiplexed, then we'd have to run all these wires all over the place. So a lot of times we multiplex to save money. We sacrifice speed for what? For money. Like using the air. The air got a pretty good deal of resistance in it. So these signals attenuate. We don't want to use a lot of power, so what do? They use what they call cell phones. What does that mean? That means we're inside a cell. The cell's only good for like a mile. And then what do? Well, they put another tower. So that's why they call them cells. You're constantly being what? Passed from cell to cell to cell. That's why they found O.J. Simpson. You know that, right? He was in the back of his Bronco using his cell phone, and they was watching him switch between the cells. Cell, and they figured out what interstate he was on just because of the way he was switching between the cells. So right now they can find you within the cell. They don't know where you're at in that cell unless you got GPS on your phone. If you got GPS, they can find you within No, you don't have to use it, but they know what cell you're in. No, right, just like that. But that's within a mile, right? You understand? That's where they found O.J. Simpson. That's before they had GPS, and he was using his cell phone in the back of the Bronco. And what was it doing? It was changing sails. He was switching sails while he was driving. So radio works great, but it only works over a certain distance, right? You understand that? So the 74151 is a multiplexer. It's a time domain multiplexer. Works great. Lasts a long time. So what do we multiplex for? Saves a lot of money. Sometimes we multiplex when we got real slow things. Odds are we're going to multiplex. Sometimes we multiplex because we have to. So Ethernet is multiplexed. They expand. Except they don't have. What's nice about baseband is they don't send the select wires. The select is inside the packet. So your IP and MAC address are inside that packet, right? You understand? Until you get to your first switch. As soon as you get to your first switch, your switch strips off the MAC, and then after that it's IP. But it keeps up with your IP and it keeps up with your MAC. So when it comes back, they say, okay, this IP matches this MAC, and that's where it actually ends up. So eventually it's going to have to get back to a MAC address. So your phone has got a MAC address that's built into the phone, and then it's got an IP address. So when I go to my house, I get a different IP address, right? You understand? I come here, I get a different IP address. So IP addresses are logical. They're set by the network. MAC addresses are built in. So this phone, that MAC address is going to follow this phone forever. And that's a 48-bit number, guys. It's 2 to the 48. The first 24 bits identifies the manufacturer, and then the next 24 bits is a computer, is a network device that manufacturer uses. So every manufacturer's got have a set of MAC addresses. When they use all, that's 2 to the 24th. What's 2 to the 24th? Big. 2 million, something too big. Of course, when they run out of those, then they get another manufacturer's ID. So now y'all know about MACs, y'all know about IPs, y'all know about dynamic IPs, static IPs, so y'all learned a lot tonight about MAC addresses. It's about networking. DNS, DHCPs, gateways. What's a gateway? That's what connects a local network using private IPs onto the internet. So you can't go to the internet from a private network without going through a what? Okay. So private IPs can be duplicated. So this company can use the same private IPs that I use because they never go out on the what? On the internet. If they do get on the internet, all your routers and everything, just strip them off. They're not legal. The dark web doesn't use DNS, right? The dark web don't use names. They use IPs. So before you can get into a dark web site, you have to know their IP address. They're not registered in a DNS server. Dark web is using IPs. So you have to know somebody that gives you the IP, or go searching, which would take a long time. 2 to the 32nd or IPv5, IPv6, that would be a lot of combinations, wouldn't it? So multiplexing. If we multiplex, we got to do what? And we do that different ways. So basically, a demultiplexer works like this. So a digital demultiplexer, not a address demultiplexer, a digital multiplexer. So what we do is we bring in the data, and then we select which data. We bring in the data over here, then we select which data to route to the right address. So what we do is we bring the select pins over from the multiplexer, and then it selects the demultiplexer. It tells the demultiplexer how to send it out. But what we can do is we sent what? We sent eight data wires we sent 8 on what? 4 wires. Right? I could send 16 on what? 5 wires. I could send 32 on 6 wires. So every time we update we don't have to update the data wire, right? All we got to update is just the number of select lines we send over. So we could do 62. So we could do 65,536 on 17 wires. 65,536 on 17 wires. If I didn't need multiplexing, then it would take 65,536, right? You understand? So you understand why they multiplex. Sometimes the hardware don't need the speed of the data. So that's why, like USB, stuff like that, they've gone to serial and it's multiplexed, right? So USB is multiplexed. That's a real neat thing. So that's a dynamic address too. So when you plug your USB stick into or USB device into a USB port, it sends out a code saying I'm here. It's just a blank packet. This comes into your host port, and it knows the IP, it knows the addresses that are assigned, and it assigns that device an address, a USB address. So these go, and y'all see it when y'all plug them in there, right? And then, of course, what's nice about that is it also can contain the driver. Used to, when we install something, it would come with a disk, and we'd install it, and then we'd install the driver. Now, USB, the driver's inside the sticks. It's really neat. They got memory in there. You plug it in, it'll come up and say what? Installing, yeah, this device, and then after that, it can communicate. Uh,
Got a lot of different USB. I
Devices.
went to this little convention and I thought it was a bracelet like that, but it's USB.
Oh, really?
It looked like a bracelet, but it's USB.
Oh, this guy here can be, you can hook this up USB, but all you do is just program it and stuff like that with it. This is a Garmin, so it's a Garmin HD, which is really I really like it. They'll see me get my text and stuff.
Yeah.
I can't talk to it. Some of the Apple Watches you can actually it's just Dick Tracy. You ever see Dick Tracy talks in his watch? You ever see anybody talking to their watch? They have them. Y'all hear? That was my watch. So here's some D multiplay. By the way, let's look up a 7442. No, let's look up 74138 again. 74138. What does it say this guy can do? Demultiplex. What they do is really, really neat. I don't have it set up. Is what they'll use like the G input. The G input is the data input. So what happens is that when the G input goes high, it decodes it. It's enabled. Then they select it, and then when it goes low, it. Y'all understand what I'm saying? Probably not. What I'll probably do is next class is I'll come up and I'll do that on electronic workbench for you next class.